Welcome to the deep dive. Today we're tackling something maybe a bit mathematical, but really important, matrix multiplication.
Yeah, it sounds abstract, but it's like everywhere.
Totally. It's humming away behind the scenes in statistics,
Yeah.
with covariance matrices, Gram matrices, things like that.
And data analysis, machine learning relies heavily on it. Even wireless communications. Think linear regression calculations.
Right. But the thing is, when these matrices get really, really big, multiplying them takes a lot of computing power.
Oh, absolutely. It can become a serious bottleneck, especially with the massive data sets we're working with now. The sheer number of calculations just, well, explodes.
Which naturally leads people to ask, can we do it faster? And, this isn't a new question. Researchers have been trying to optimize this for ages.
Right. Strassen's algorithm back in, 69? That was a huge moment.
Yeah, 1969. It was kind of mind-blowing, showing we could actually multiply matrices with fewer steps than the standard way. It sort of opened the door.
Definitely opened the door for general matrix multiplication. But today, we're zooming in on something a bit more specific, but super common. Multiplying a matrix by its own transpose. Usually written x times x transpose or XXT.
Okay, XXT. Why focus just on that one?
Well, it just pops up all over the place,
Yeah.
figuring out relationships in data, training AI models. It's fundamental. So even a small speed up for just XXT could have, a really big impact practically.
Gotcha. So that's our mission for this deep dive then, exploring a new way to calculate XXT.
Exactly. There's this new algorithm called RXTX. And what's really interesting is it wasn't just thought up by a person. AI played a big part in its discovery.
AI discovered algorithms.
Wow.
Okay, and our sources today are research excerpts that detail this RXTX algorithm, right?
That's right. Laying out how it works and what it can do.
Okay, cool. So before we jump into RXTX itself, what was the best way people were doing this XT calculation before? What's the baseline?
So the state of the art, especially for standard numerical matrices, was basically adapting Strassen's algorithm.
Ah, okay. Using the general purpose FAST method.
Pretty much. They treated XXT like a general matrix multiplication problem, but they cleverly applied Strassen's approach recursively, breaking the big matrices down into smaller 2x2 blocks and applying Strassen's method to those.
Right, sort of leveraging a known FAST technique for this specific case.
Exactly, a smart application. But RXTX comes at it differently.
Okay, how so?
Well, RXTX is presented as a completely new thing designed specifically for XXT right from the start.
And this is the AI discovered part.
Yeah, it came out of this mix of machine learning and some pretty advanced combinatorial optimization. So less aha moment from one person, more AI-guided discovery.
Fascinating. So what's the actual innovation? What makes it potentially faster?
The core idea really is how it breaks the problem down. Instead of those 2x2 blocks like the Strassen adaptation,
Yeah.
RXTX uses a recursive strategy based on 4x4 blocks.
Okay, 4x4 instead of 2x2. Let's unpack that a bit. So both methods break the big problem into smaller chunks, right, recursively. The old way used 2x2 blocks, making, 4 recursive calls each time. How does the 4x4 approach of RXTX compare in terms of, the number of steps?
Right, so that's the key trade-off. With the 4x4 blocks, RXTX actually makes 8 recursive calls.
8. That sounds like more work initially.
It does, yeah. But the flip side is it only needs 26 of what they call general product calculations at each step. Think of those as the basic multiplication operations.
Okay, 8 recursive calls, 26 general products. How did the old method compare?
Well, the comparison gets a little tricky because of the different block sizes, but effectively the previous method, based on those 2x2 blocks, translates to meeting something like 16 recursive calls at a comparable depth, but needing the equivalent of 24 general products.
Okay. So more recursive calls for RXTX, but slightly more general products needed. No, wait. Fewer general products needed for the old way. 24 versus 26.
Sorry, let me clarify. RXTX. 8 recursive calls, 26 general products, the previous best, Strassen-based effectively. 16 recursive calls, 24 general products when comparing equivalent levels. So RXTX uses fewer recursive calls at the fundamental 4x4 level, but more general products per step. But the real win shows up when you look at how things scale.
Ah, okay. We're getting into asymptotic complexity now, looking at really, really huge matrices.
Exactly. That's where RXTX pulls ahead. The research states it gets about a 5% reduction in the asymptotic constant for the number of multiplications.
Right. That constant tells you sort of the leading factor in how the cost grows.
Precisely. So for RXTX, that constant is roughly 26 divided by 401, which is about 0.6341.
Okay.
Whereas the previous method's constant was 2 divided by 3, so about 0.6666.
So 0.63 versus 0.66, that 5% difference, I mean, it sounds small.
It might sound small, yeah. But when you're talking about these massive computations, like training huge AI models or complex simulations, that 5% can translate into saving, days or even weeks of compute time and tons of energy. It's actually a pretty big deal at that scale.
Right, okay. That puts it in perspective. The sources give some formulas for this, don't they?
They do. For RXTX, the number of multiplications, let's call it Rn, is roughly 8 times Rn4 plus 26 times Mn4. Mn4 is just the cost of a general multiplication for that smaller N4 size.
And that leads to the asymptotic result, Rn, being proportional to 2641 times Mn.
Yep. And for the old way, Sn was 4 times Sn2 plus 2 times Mn2, leading to Sn proportional to 23 Mn for large N.
So the formulas kind of capture that recursive structure and how it scales.
Exactly.
But hang on, it's not just multiplications, is it? There are additions too. How does RXTX fare there?
That's a really crucial point. Often the focus is purely on multiplications, but additions add up too, cost time, and RxTX actually scores well here too. Yeah, the research shows it uses an optimized scheme that also reduces the number of additions needed. They mention cutting it down from 139 additions to just 100 using specific algorithmic steps they developed.
Wow, 139 down to 100? That's quite a drop in additions as well.
It is. So when you look at the total operations, multiplications, and additions, well, the formulas get pretty hairy. R plus N and S plus N, they call them.
Okay, maybe let's not get lost in the mathematical weeds there.
Probably wise. But the takeaway is RxTX is designed to be more efficient overall, considering both types of operations.
And this isn't just theory, right? They actually tested it.
They did. They ran experiments comparing RxTX on a pretty big matrix, 6144 by 6144.
Okay, that's a decent size. What did they find?
The results look pretty good. They found RxTX was, on average, around 9% faster than a standard, highly optimized library routine, a belay-less routine that's specifically designed for XXD.
9% faster in practice. That's noticeable.
Definitely. It shows that even for matrix sizes used in real applications today, not just theoretical astronomically large ones, there can be a tangible speed up.
Does it say, like, what's the smallest size where RXTX starts winning?
They mention it's a bit hardware dependent, which makes sense. Different chips, different performance characteristics.
Sure.
But their analysis, looking at one of the figures, suggests RxTX could potentially beat recursive Strassen for sizes, maybe Engel 256 and up. And it could even beat the simple schoolbook multiplication method for n bigger than maybe 32 if you use optimal cutoffs, meaning you switch to simpler methods for the really tiny subproblems.
Okay, so it shows promise across a range of sizes, depending on the comparison. This AI discovery process, though.
Yeah.
Let's circle back to that. How did the AI actually, find this?
It's pretty neat, actually. They use this combination approach. First, there's reinforcement learning, the AI learning by trial and error. This RL agent guided something called a large neighborhood search. Its job was basically to propose lots of different ways to break down the XXT calculation into simpler pieces, specifically rank 1 bilinear products.
Rank 1 bilinear products. Okay. What are those in simple terms?
Imagine them as, very basic multiplication building blocks. They involve multiplying simple combinations of elements from the original matrices. The RL agent wasn't necessarily finding the perfect set immediately, but it was good at suggesting a whole bunch of potentially useful building blocks.
So the AI is brainstorming building blocks. Then what?
Then comes this two-level MIL-UP pipeline. MIL-UP stands for Mixed Integer Linear Programming.
Right. That sounds like heavy-duty optimization.
It is. It's a very structured way to find the absolute best solution from a set of possibilities under certain constraints. The first MIL-E part, MIL-EA, figures out all the mathematical connections between the building blocks the AI suggested and the actual target answers needed for XXT.
Okay, mapping connections.
Then the second part, MIL-PB, takes that map and finds the absolute smallest set of those AI-suggested building blocks that can still be combined to correctly calculate everything needed for XXT. It's like finding the most efficient recipe using the fewest ingredients from a big pantry the AI stocked up.
That's a great analogy. So the AI suggests possibilities, and the MIL-UP finds the leanest, most efficient way to use them.
Exactly. They contrast this with, say, the alpha tensor approach, which explored a much more abstract mathematical space. Here, it seems like they focus the AI on generating these fundamental product components and then use the power of MILP solvers, which have gotten really good recently, to put them together optimally.
Right. They gave a little 2x2 example too, didn't they?
Yeah, just to illustrate, the AI might randomly suggest some basic products, and the MILPE figures out how to combine the minimum number of those to get the target XXT result for that tiny case.
It really feels like a new way of doing mathematical discovery, combining AI's exploratory power with these strong optimization tools.
It does seem like a powerful combination. And of course, they acknowledge their funding sources too, which is standard practice.
Right, important to mention. Okay, so let's wrap this up. What's the main thing listeners should take away about RXTX?
I think the core message is we've got this new algorithm, RXTX, cooked up with help from AI that's specifically faster for calculating X times its transpose.
Faster how?
By cutting down on both the multiplications and the additions needed. And critically, this isn't just theoretical. They've shown practical speedups, like that 9% improvement in their tests.
And given how often XXT is used,
Yeah.
that's significant.
Hugely significant for any field that leans heavily on linear algebra, data science, machine learning, scientific computing. Making this fundamental operation faster can unlock a lot of potential. Save time, save energy.
It really points to the potential of AI, doesn't it? Not just using math, but helping us find new math, new algorithms.
Absolutely. It makes you wonder what's next.
Exactly. That's maybe the final thought to leave people with. As AI gets better at this kind of discovery, what other basic fundamental algorithms, things we thought were maybe solved, might be due for an AI-driven optimization? Could we see similar breakthroughs in sorting, searching graph problems? It's definitely something to keep an eye on. Thanks for digging into this with me.
My pleasure. Fascinating stuff.